Okay, so welcome back, everybody. So last time we ended with a statement of some general properties of contour integrals, but we actually hadn't computed a single one yet, and so that's what we're going to do today, and that's why this lecture and the next lecture are important because they're going to kind of form the meat of most of the examples that you see from my end of computing contour integrals. So let me just remind you all from yesterday's lecture, the definition of a contour integral is the following. So if we have a function that is piecewise continuous on the curve itself, so if we have contour C is described parametrically in this way that we talked about before. So Z is some function of t, and maybe contour generally looks maybe something like this. Okay, this parameter t lives in the closed interval from a to b on the real line. And so if f is continuous on a contour, or piecewise continuous on the contour, what it means is this, that f of z of t is piecewise continuous on this interval ab, and that's the usual definition of piecewise continuous, because now this is a function of a real variable t, right? So we say f is piecewise continuous on C. Then the contour integral of f along this contour C is this particular line integral we've defined in this way. This is the integral from a to b of f of z of t times z prime of t dt. Right now, a couple things to note here. One, so this is perfectly, all this is fine, so long as f is piecewise continuous on the contour C. This, by definition of contour, this z prime is good to go. It's piecewise continuous on the closed interval a to b, and so everything that's the integrand here, everything underneath the integral sign here, is perfectly fine for this thing to be well defined. This is an integral in the Calc 1 sense, right? This is because this is just an integral from a to b, a and b real numbers, of some function of a single variable t dt, right? So it's perfectly well defined and something that you're used to. And it turns out that this is invariant with respect to reparameterizations of C, and you can do this with the reparameterization setup that we talked about during the last lecture. Okay, so this is the definition of a contour integral. So when you're actually going to compute, right, this is what it is you're doing. Now, of course, as we go along, and you have computed a few of these things, then you may want to know some more general properties in order to make further computations simpler. And so these are some properties that I stated. I didn't prove, but my hint on how to prove these, if you're interested, is that ultimately a contour integral is a Calc 1 integral, right? It's just a very specific one set up in a specific way. And so the reason that these hold is the same reason that these corresponding facts held for line integrals, okay, coming from Calc 3. Okay, and so you had all these facts in Calc 3 for line integrals, and so you get these things for contour integrals as well. Okay, but let's actually compute. So if I'm actually going to compute here, let's pick an example. So here's first example, coming straight from the textbook. So let's say, so let C be the right half of the circle of radius 2 centered at the origin. Modulus of Z is equal to 2 from, say, Z equals minus 2i to Z equals 2i, right? Okay. Compute the contour integral over C of Z bar dz. So this is what I want to compute. Okay, so I want to compute this thing. All right, so what do we need in order to compute this? Well, let me flash my definition back on the screen here. So in order to compute a contour integral, I need this parametrization of the contour C. Okay, so just like when you're doing line integrals in Calc 3, you needed the parameterization of the curve in order to actually do this computation. So we need this parameterization, this way of expressing this contour in terms of a real parameter. Of course, we don't have to use the parameter t. We can use whatever naturally arises here. And so C is the right half of this circle, right, from minus 2i to 2i. What does that look like? So this, of course, looks like, so here's, we'll say minus 2i. The right half of the circle of radius 2 centered at the origin looks like this. This is 2i. Okay, so this is my curve C. Of course, it's already, I have an indicated orientation here. So this is my curve C. So now I need a way of representing this contour. So first, my question is it a contour? Yeah, right, it's definitely a contour. So this thing is definitely a contour. It's not even that, this is not even that complicated. Okay, it's not a closed contour or closed curve because it has two endpoints. It doesn't close up like a loop, right? So this is definitely a contour. What do I do here? I want to come up with a parameterization for this thing. So how can I do that? Well, right, in some of these problems, maybe the curve is nasty, or maybe just the way that the curve is defined is you're given it as a parameterization rather than a picture. Okay, so in that case, well, you would already have the parameterization in front of you. But in this case, say that all you're given is this picture or this description and nothing else, right? Well, then you have to come up with the parameterization on your own. So this isn't too tricky for part of a circle here, because we know that this is part of circle radius 2. So then coming up with a description of this thing in terms of polar coordinates is always easy. So z is 2e to the I theta. All right, this is a nice description of this in terms of a single parameter, where that parameter lives where? What's kind of the easiest way to describe this? Well, the easiest way to describe this is, well, that theta is taking on values between minus pi over 2 and pi over 2. Right? It's kind of the easiest description here. And so there is my description of my curve in terms of a single real parameter, theta, right? So I'm not having to use t here. I can just use theta. So there's nothing wrong with this representation of my contour C. Okay. So now, yet again, let's bring back our definition. So if I want to compute this thing, so if I want to compute the contour integral over C of z bar, right, conjugate of z here, using this, then what do I do? Well, according to this would be the integral from my parameterization. The parameter here, theta, lives between minus pi over 2 and pi over 2, so this is the integral from minus pi over 2 to pi over 2. Okay, now, typically, as we'll see in some of the upcoming examples, we have to ask ourselves questions when we're in more complicated situations where maybe the thing here is nasty, right, at a certain region, or maybe it crosses, say, a branch cut for a particular branch of the function that you're talking about. There's all of those considerations can come in general, and we're going to see plenty of examples of those. But in this case, we're dealing with an integrand that is good to go here. I don't have to worry about it anywhere along this curve. In fact, checking before I'm even doing this, this thing is perfectly, what I'm about to write down here is piecewise continuous, at least on this whole contour. In fact, it's actually just continuous. It's good to go. Okay, and so it is f of z, which is z bar, with the parameterization plugged in, right? So it is 2e to the I theta, and I am taking the complex conjugate of that. Right, so that's what this is, times the derivative of z, with respect to t, or with respect to the parameter that you've written it as. So here we have z that is, we're describing it as z of theta. And so z prime here is with respect to theta. What is the derivative of this with respect to theta? Well, for now, I'm just going to write this as 2e to the I theta prime, because I'm taking the derivative of this thing, right, d theta. Okay, that is how I'm doing that integral. Okay, well, I can make my life a little easier here. So 2 right here and 2 here can be pulled out. You can pull 2 out of this complex conjugate business because it's a real number. So 2 times 2 is 4, so this is 4 times the integral from minus pi over 2 to pi over 2 of e to the I theta bar times what is the derivative of e to the I theta with respect to theta? Well, I don't have room to write it here, so I'm just going to write e to the I theta prime since I've pulled this constant out of that derivative. And this is d theta. Okay. So what is this equal to? So first of all, I can say, well, e to the I theta bar, what is that? What's e to the I theta bar? So I'm taking the complex conjugate, not of I theta, I'm taking the complex conjugate of e to the I theta. So this would be cosine theta minus I sine theta, which is cosine of minus theta plus I sine of minus theta, using the fact that sine and cosine are odd and even, right? Or even and odd, respectively. Then this is actually just e to the minus I theta, right? Okay, so that's e to the minus I theta. What is e to the I theta prime? Well, you know how to take care of this, right? This is just I e to the I theta. You have plenty of practice taking derivatives of these complex functions by now. Okay. And so, putting these things together, I get that this is 4 times the integral from minus pi over 2 to pi over 2 of e to the minus I theta times I e to the I theta d theta. Okay. But I is just complex conjugate. That can be pulled out of this integral. E to the minus I theta times e to the I theta is e to the 0, which is just 1. So this is actually 4i times the integral from minus pi over 2 to pi over 2 d theta. Okay. Which is equal to, this is just theta evaluated from, this is 4i theta evaluated from minus pi over 2 to pi over 2. So it's pi over 2 minus pi over 2. So that is pi. So this is 4 pi I. Okay. All right. Now, you've gotten an answer for computing one of these contour integrals. So then you naturally might have a question. Say, like, what does this number mean? So unfortunately, of course, just like we didn't have a 100% straightforward description of what, say, the derivative, the complex derivative of a complex function was, or what it was representing, we similarly don't have a 100% straightforward answer to the question of what exactly is this number telling you. As I said, when I talked about how this is a line integral before, line integrals had some interpretation if you thought of them talking about the integrating a mass density function along a piece of string or a piece of wire or something. The path of which is marked out by the contour, but we don't have to get into any of that kind of stuff. Just don't worry about the interpretation of this number for now. Okay, we are going to have particular interest in some of these numbers. So sometimes we are going to we're going to ask questions about what specifically these numbers are and say when this integral is equal to 0. We're definitely going to ask questions like that, but that's for a little bit later. Okay. All right. Now, you might also notice an example. What is using the same C? So using the same C as before. What is the contour integral over that C of 1 over Z dz? Okay. So an example of how you can compute this without actually having to compute it is we know previously that over that exact C, the integral of Z bar dz is 4 pi I. Okay, so we knew this from our previous example. Also, Z times Z bar is equal to the modulus of Z squared. We always know that. But this is equal to 4 when the modulus of Z is equal to 2. So note this. Along this particular curve, because you are describing something very nice here, right? That is, these points are not just any points. They are points that are exactly distance 2 from the origin in the complex plane. Okay. And what does this mean? It means that on the circle, modulus of Z is equal to 2, we have that Z bar is the same as 4 over Z. Okay. And so, using this, the integral of Z bar dz is equal to 4 pi I. This means that the integral of 4, so this is over C, the contour integral over C of 4 over Z dz is equal to 4 pi I. I can factor the 4 out and cancel it, so that the contour integral over C of 1 over Z dz is pi I. Okay. So there I use the fact that I can pull constants out of this contour integral to find what this thing was without actually having to compute it, just based on what I'd already computed. Note that this type of trick is heavily dependent on exactly what this curve C is. Okay, and so this kind of trick of being able to use, say, this to compute this is something that could be done in this case, but might not be able to be done on some other contour. So in general, okay, the value of contour integral, okay, of some function depends both on f of z, that is the values of the function f of z, and the contour c. Okay, meaning that keeping the integrand the same and changing the contour in general is going to change the value of the contour integral. Okay, so in general, this is going to change the value of the contour integral. Okay, let's actually see an example of this. One quick note is that if we write f of z and we write it in the usual way as u plus iv, sometimes what we can do is we can actually use x or y as one of the parameters here. Okay, sometimes, so, okay, if we write z as x plus iy, as we always do, then sometimes we can apply our definition of the contour integral using either x or y as the parameter. Okay, we saw an example of this when I wrote out my the very first example of a contour that we talked about. So first of all, let's do a setup here. I'll use the same notation that is used in the textbook for this example, so that if you're following that, there's some consistency. So consider the following example. So let's say that we have XY plane here. Okay, and I'm going to talk about two paths. Okay, so I'm going to talk about two paths. So one is the path that goes up this y-axis to the point I, okay, and then goes over to this point I plus 1, or 1 plus I. Okay, and so we have a path C that goes from this point, which is, we'll call that O for the origin, up to, actually I'll call this C1 since I'm going to have another curve. So C1 will be going up this y-axis to the point I, and then across to the point 1 plus I. We'll call this point I the point A. We'll call this point 1 plus I the point B. Okay, and so C sub 1 is that whole curve. Okay, and now we will consider the other curve that just goes directly there. So C sub 2 goes directly from O to B. Okay. All right. So let's compute two things. So I want to compute, so let's say f of z is, we'll give it in terms of x and y. We'll say it's y minus x minus I times 3x squared. Okay, so we're thinking of z as being x plus iy here. Okay, so here's my f of z. And I want to compute two things here. I want to compute the integral along c sub 1 of f of z dz, and the integral along c sub 2 of f of z dz. So I want to compute contour integrals along these two different contours. Okay. So let's compute this one first. If I wanted to compute that one, note from these previous properties that I mentioned, if you have a curve that is the concatenation of two curves, so if I'm laying the curves end to end and it traverses c sub 1 and then c sub 2, then I can compute the integral of along that contour a function as a sum of contour integrals, where I've broken it up along those pieces. Okay, and so how does this work here? So there's this piece and then this piece, right, for c sub 1. C sub 2 I don't need to break up because it has a nice, it's going to have a nice convenient way of describing that. But for c sub 1 I can break that up entirely. And so let's do exactly that. Note by that property the integral along c sub 1 of f of z dz is equal to the integral along this piece, which is the line segment OA. So we'll say it's the integral along the line segment OA of f of z dz plus the integral along the line segment AB. Right, so this is the integral along the line segment AB of f of z dz. Okay. Okay, so that's nice. Now I need to compute these integrals separately, right? So in order to compute this, I compute these integrals separately and then just sum the results. Okay, so how do I compute this thing separately? So first, I need a description, a parametric description of this segment OA. So how can I do that? Well, the idea here is OA, parametrically, how would I describe that? Well, really, x is 0 this entire time. The only thing that changes is y. So 0y is the parametric representation of what's going on here. And so the way of thinking about that in terms of z, this is 0 plus iy, okay, where my parameter y goes between 0 and 1. Right? So this is what I meant by viewing this thing parametrically, where I can actually use, in this case, y as my parameter, okay, describing that path. Okay. And so, along this path, f is pretty easy. Note, along OA, f of z is equal to, well, along OA, f of z, or sorry, x is just always 0. Right? So x is always equal to 0 along this path. And so f of z, which looks like y minus x minus I 3x squared, becomes y, right? So along OA, f of z is equal to y, right? Where y is in this closed interval 0 to 1. And so f of z is actually extremely simple, okay, along OA. And so the integral along this segment OA of f of z dz is equal to, well, f of z is just y there. All right, so in my parametrization, my definition for contour integral, this is the integral from 0 to 1, right, of f of z of t. Well, here, that parameter t is actually y, so this is f of z of y, which is just y, right, times the derivative of z of y, right? So this is here. Maybe let's rewrite this. Let's say f of z of y here, right, times z prime of y dy. This might give you a better understanding of what's happening here. So this is just from my definition of contour integral. Okay, so this is the integral from 0 to 1. F of z of y, as we saw here, is just y. And z prime of y, well, so that's the derivative of this z parametric description with respect to the parameter y. So derivative of that is just I. Right, so this is I dy. Okay. So then I can pull that I out. So this is I times the integral from 0 to 1 of y dy. The integral, of course, of y dy is y squared over 2. So this is I times y squared over 2, evaluated from 0 to 1. So evaluating 0 yields 0, and so I'm only getting the top one. So this is 1 squared over 2. So this is I over 2 is what I get from that. Okay. All right, so let's see about the other segment. So we've only done half of this contour integral. So along AB, first of all, how do I describe AB parametrically? So z is equal to what? Well, x now is varying, of course, right? X is changing between 0 and 1 here. So x is generic between 0 and 1. But what is going on in y? Well, y is not changing at all. Y is just 1 the entire time. So if z is x plus iy, y is just 1, so this is just x plus I, right? And x is between 0 and 1. Okay. All right. So if that is the case, well, we know that y is equal to 1 here, right, along AB. And so, thus, along AB, f of z is equal to, so x is general, right, and here's my f. X is general, but y is equal to 1. Okay, so what is this? This is 1 minus x minus I 3x squared. Okay, oh, a little bit off the camera there, yeah. So this is 1 minus x minus I 3x squared. Okay. All right. And so if I'm looking at a description now in terms of this parameter x, I'm doing this contour integral in the following way. So this is that's the integral along AB of f of z dz is equal to the integral from 0 to 1. Now this is describing where the parameter x lives of f of z of x, right, times z prime of x dx. So going back here for a second, here's here's z of x. So if I take the derivative of this with respect to x, I just get 1. Right, so I just get 1 here. Along AB, f of z of x here is 1 minus x minus I times 3x squared. Okay, and so this becomes the integral from 0 to 1 of 1 minus x minus I 3x squared times 1, which is z prime of x dx. Okay. All right, well, we can do this term by term here. All right, so really this is two integrals, so this is like the integral. Or I can just do this. I'm just going to do this term by term here. So this is the integral from 0 to 1 of 1 minus x minus I 3x squared dx. I'm going to do this term by term to get this is x minus x squared over 2, right, minus the integral of 3x squared is, of course, x cubed. So this is minus I times x cubed. And I'm evaluating from 0 to 1 there. Right? So doing this evaluation quickly, what do I get? Evaluating at 0, I get 0 in each case. So then I just get the top term. So this is 1 minus 1 squared over 2 minus I times 1 cubed. Right? So this is 1 minus 1 half, which is 1 half minus I. Okay. Thus, the integral that we wanted to compute originally, we bring it back. The integral along this contour c sub 1, okay, which is this arc, right, okay, that had those two pieces. It's the sum of the integral along OA and the integral along AB. So the contour integral along c sub 1 of f of z dz is equal to this contour integral along OA of f of z dz plus contour integral along AB of f of z dz. But we found that the one along OA was I over 2, and the one along AB is 1 half minus I. Okay, and so adding these together, this is 1 minus I over 2. And so the contour integral that we're first looking at is 1 minus I over 2. Okay. So now, going back to our example, I had another curve here, right, that I wanted to compute the contour integral of. So this one. right? So this is the segment OB, right? Of course, I don't need to write that because C sub 2 is just exactly that segment, so I just need to come up with a nice parametrization of C sub 2 here. Okay, so if I'm looking at C sub 2, first of all, what is this curve? This is just a segment of the curve y equals x here, right? And so really, what I have here is along C sub 2, z is equal to x plus xi, where x is just going between 0 and 1, right? So again, I was able to use either x or y as my parameter. Okay. So here, what do I get when I'm computing this integral of f along C sub 2? Well, I need to plug in I need to plug in, sorry, x, or I need to plug in z of x here, right? So I'm viewing this as z is equal to z of x. So this is the integral from 0 to 1 of f of z of x times z prime of x dx here. Okay. And so let's recall what my f was. So f is given here. So I'm plugging in z that looks like x plus ix. So this becomes x minus x. That's 0. So it's minus I 3x squared here. Right? So f of z of x is just minus I 3x squared. Okay, and z prime of x is 1 plus I. Okay, dx. All right. And well, I can actually bring out minus I times 3 times 1 plus I. Right, so this is minus I times 3 times 1 plus I times the integral from 0 to 1 of x squared dx. Okay. Well, maybe if you like, I can leave the 3 in. Let's do that. Let's leave the 3 in because the integral of 3x squared is x cubed. So let's leave the 3 in here. And so and so what is this? What is minus I times 1 plus I? I get minus I. Minus I times I is minus minus 1, so that's plus 1, so this is 1 minus I. So I get 1 minus I here times the integral from of 3x squared dx is just x cubed. So this is x cubed evaluated from 0 to 1. So this is 1 minus I. Okay. So my integral along C sub 2 is 1 minus I. My integral along C sub 1 is 1 minus I over 2. So it's actually half. Going back to our picture, let's fully realize what this means. I have two curves, C sub 1, C sub 2, two contours. Right? Both of them have the same initial and terminal points. Okay. But this f, using the same f for both of these integrals, what I get is that even though both of these contours have the same initial and terminal points, the value of these contour integrals is different. Okay. That is to be expected based on what I said originally, immediately before this, that this in general depends on the curve that you choose. Okay, so even when the contours are nice enough that they have the same initial and terminal points, okay, that statement is still true, that this depends on the path chosen. Okay, so note we have just shown that even though C sub 1 and C sub 2 had the same initial and terminal points, the value of these contour integrals were not the same. Okay, even though they had the same integrand function. So we had contours, say, that look like this, right? Now you might be having some flashbacks to Calc 3 questions, because this might trigger the particular response here, which is, well, do there exist functions for which the integrals along all these paths are the same? Okay, so big first question we're going to ask here is, do there exist functions f of z such that the integral over c of f of z dz is independent of path? What does independent of path mean? Independent of path means that as long as the initial and terminal points are the same, this quantity is the same. That was clearly not true for the function that we just did, but do there exist functions for which this is true? That is basically if I have initial and terminal point A and B, as in this picture, I could have chosen any of these contours and this value would have been the same. Do there exist functions like that? Hold on for 1 second. Okay. So, the question is, one, does this depend just on curves? Okay, or does this, is there some property that the function can have that would tell us this, right? So maybe a secondary question here is, are there conditions that are sufficient to guarantee this? And what conditions would these be? So conditions, say, on F, on C, etc. Okay. Okay. So, let's let us maybe, before I answer any of these questions, I'm going to be piling up a list of questions that are related to this that are going to be not exactly the same, but they are related to these and other questions that I'm going to state here. So we are going to give affirmative answers to these questions. You will have answers to these questions, just not at the moment. Okay. Because I'm going to push it off, because this is going to be basically one of the central things that some of the big named theorems that we talk about actually address. Okay, so that's basically what those theorems are going to say. So you will know in the next couple days answers to questions like this. Let's see an example of one of these, though. So for now, let's just look at the following example. Let us just look at the following example. To give one particular instance of when this is actually this actually works out pretty nicely. Okay. So, consider the following example. Um, so, consider the case of attempting to compute the contour integral along C of d, or of z dz. Okay, where C is any arbitrary smooth arc that we'll describe as in the usual notation. So Z is Z of t is my parametrization, and t lives between real values a and b. Okay. Okay, and this C is some arbitrary smooth arc that we'll say goes from some point z sub 1 to some point z sub 2. Maybe it does something like that. Okay. And so if I wanted to compute this, of course, just by definition of contour integral, my contour integral of z dz is going to be the integral from, I can go ahead and put the integral from, say, a to b here of z of t times z prime of t dt, right? Because here our f of z is just z, right? And so f of z of t is just z of t. Okay. All right. And so this particular form is really, really nice. Okay, this is actually going to be the key to the whole thing. But note that the derivative, right, d dt of z of t squared over 2 So if I'm looking at this thing and I compute the derivative of this quantity, what do I get? I get exactly z of t, z prime of t. And so I can use the fundamental theorem of calculus here. Right? So by fundamental theorem of calculus, I can rewrite this. Thus, my integral over the contour C of z dz is the integral from a to b. I'm going to go ahead and just rewrite this out of z of t, z prime of t dt. Okay, and this is the integral from a to b of this is d dt of z of t squared over 2, right, dt. And by fundamental theorem of calculus, right, this is just z of t squared over 2 evaluated from a to b. Okay, so this is z of b squared, right, over 2 minus z of a squared over 2. Okay. But of course z of b is just, or z of b is just the second endpoint z sub 2, and z of a is just the first endpoint z sub 1. So rewriting this in a quicker way, this is z sub 2 squared minus z sub 1 squared over 2. Okay. Now, what is it that's important about this form here, right? Well, this actually only depends on these endpoints. Right? Note, this means that the value of this contour integral only depends on its endpoints. And so we see an example of exactly the case that we were just describing in the previous question I asked. Are there examples of functions, where it doesn't actually matter, right? What curve you pick, all that matters is the endpoints. And yes, the example is yes, and here's an example of such a function. F of z is equal to z. Okay. And so this means that this value only depends on the endpoints, and so actually it wouldn't have really mattered what C looked like here, right? C could have looked like that, could have looked like that, could have even looked like this, right? Doesn't really matter. The endpoints are all that matters here, okay? So that is the first thing to note. Okay. When we have this, when we have a case like this, it's customary to actually, so when this is true, notation for this becomes the following. So we would write this contour integral as the integral from z sub 1 to z sub 2 of f of z dz. And now you understand why notation like this would make sense in this case, because otherwise it very much depends on what path you're taking to get from z sub 1 to z sub 2. But if you're in one of these instances where all that matters is the endpoints themselves and the path you take doesn't matter, then there's no ambiguity here in writing this instead of this as a contour integral. Okay, so that's the first thing you note. But what is something else that's going on here, right? So note also what happens if C is a loop? So what happens if C is a closed curve in this particular example? So here we have a curve C, and z sub 1 is equal to z sub 2. Well, then in this case, the contour integral of z dz is equal to z sub 1 squared minus z sub 1 squared over 2, which is 0. Note, this is true for any closed curve. We didn't make any further assumptions. So this fact that this integral of this particular function is 0 for any closed curve is pretty amazing when you think about it, because, well, this could have been anything, right? This I could have been dealing with something like this. I could have been dealing with something like this, and so on, right? I could have been doing all kinds of crazy stuff. As long as I was, that looks a little unsmooth. Maybe at that point that looks a little sharp. Okay, but this is the idea that this is actually true for any closed curve. Now, you might have seen some conditions that involved this stuff in path independence coming from Calc 3, and you may remember some of those. They had a physical interpretation, so in terms of conservation laws. So this is where the notion of a conservative vector field was typically introduced. So in Calc 3, you ultimately became interested in not just integrating functions over curves, you integrated vector fields over curves. And there were properties that those vector fields could have, namely there's the property of it being conservative. And if you were dealing with a conservative vector field, and you might recall that meant that it was the gradient, that vector field arose as the gradient of some other function. And so if that was the case, the vector field was considered conservative, and that led you to facts that are very similar to these things that we're touching on now. And we're going to see how all that stuff, or we're going to see the interplay between all those things. And so I have another question. All right, so question 3. Is there a condition say on f that guarantees that the integral along contour C of f of z dz is equal to 0 for all closed contours C. This is question 3. And question 4 here, is this condition related to the previous 2 questions? So this is just a shorthand way of saying, remember my previous 2 questions. Where did I put my sheet? Oh, here we go. So my first 2 questions are, do there exist functions that are independent of path? Are there conditions that are sufficient to guarantee this? Is there a relationship between being path independent here and this being true for any closed contour here, right? That the contour integral of f along any closed contour is 0. Okay, so the question is this related to what we were just talking about? Quick answer is yes, these things are related. But in general then, we are very interested to know when the integral along a contour of f of z dz is equal to 0 for some closed contour, or simple closed curve, right? So for some closed contour C. Okay, and this is going to be a central question going forward, and we're going to have a big named theorem that addresses exactly this question. Okay, so we're going to be very, very interested in when we're dealing with something like this. Okay. But you might have a complaint, right? You might have a complaint here. And the complaint that you might have is if you wait and go back to this example, I assumed that C was an arbitrary smooth arc. But that's nicer than a contour, right? Because a contour is a piecewise smooth arc. So everything we've been doing, all these pictures I've been drawing, were of smooth contours, right? Okay. So, what if C is an arbitrary contour? Instead of a smooth arc? Well, what's the difference here, right? Well, the difference here is that instead of those pictures, your pictures would look like this, right? You would have a loop that maybe looked like this. So you have these points, okay, that are corners. But of course, if that is my contour C, then this contour, while it itself is not necessarily a smooth arc, these pieces are smooth arcs. So I would have a piece, if this is what I'm going to be calling my endpoints here, then I have the piece C sub 1, C sub 2, C sub 3, and C sub 4 in this case, right? And in general, C is a finite, it's a finite amount of such smooth arcs, right? Okay, and so the idea is that I could write C as, C sub 1 plus C sub 2 plus and so on all the way up to some C sub n here, so that when I'm computing this contour integral over f of z dz, which of course for us is, in this example, is just z dz, right? Well, when I'm doing this, because of this fact and because of this property of the contour integrals, I can split this integral up, and this is then the sum, right, from, let's not use I, let's use k here, so k equals 1 to n of the contour integral c sub k of z dz, but we know what those are, right? In fact, I can rewrite this, if you like, using this new notation. This is the sum from k equals 1 to n of the integral from, if I'm calling these like, if this is z sub 1, this is z sub n, right? So if z sub 1 is equal to z sub n here, this is like z sub 2, this would be z sub 3, z sub 4, and so on. Okay, so then this would be the integral from z sub k to z sub k plus 1 of z dz. And so what we ultimately end up with here is this partial sum. So the sum from k equals 1 to n. We know what these are, right? For each of these pieces, we know how to handle this, right? So for each of these pieces, this is actually just the sum of the things we're finding from the individual terms. So this is z sub k plus 1 squared minus z sub k squared over 2. But this is a telescoping series. So this is a telescoping series. And actually what I get is the last, this is z sub m plus 1, we'll call this, to keep this notation going. So this is z sub m plus 1 squared minus z sub 1 squared over 2. Okay. And so, using the fact that this series is telescoping, and all the middle terms cancel out, so we just have terminal minus initial here. So, the integral over c of z dz is equal to 0 if c is any closed contour. And so your complaint, while it was a good complaint to notice that I actually hadn't shown this for a contour yet, we smoothed that out by passing to the smooth pieces. The reason I wanted you to see this is because usually that's exactly how these arguments go. So in order to pass, from just a smooth arc to an arbitrary contour, you use the fact that a contour is a piecewise smooth arc, and so it is made up of some finite number of pieces. And so typically what you'd want to do is figure out, if you're happy on smooth arcs, then a contour is just some finite number of those things, right, tacked together. And so you want to make an argument like this. You want to pass to the smooth arc pieces where you're happy and see if you can wrangle things to work out in the way that you want them to. Okay. So that's that. All right. So next, all right, so as I said, we are going to return over and over again to this, so we are interested in these sorts of things, as I noted before. Okay, this is going to form central questions for us going forward. All right. Next, that's a nice batch of examples to kind of get you going with this stuff. The next batch of examples are examples involving branch cuts. So this is examples involving branch cuts. So I defined branch cuts before. So what is a branch cut? So a branch cut is, this is, a part of a curve or line used in the definition of a branch of a multi-valued function. So that might not tell you a whole lot, just hearing those words in that particular form. Okay, but we're going to see exactly how this works. Okay, the basic idea here is how do I deal with integrands involving points along the contour C where things are messy. Okay. Okay, so in general, when we're talking about branch cuts, right, we're talking about particular ways of defining branches of multivalued functions. In the context of contour integrals, where this comes up is one, sometimes you're wanting to integrate this multivalued function and there's some parts of your curve where there's some ambiguity here. Okay, and you have to be careful of how you address that. Another example, which is something we won't get into until the next section, which is we are going to be talking about whenever you bring up integrals, necessarily you're typically going to want to talk about antiderivatives, right? Because we know the relationship between integrals and antiderivatives in Calc 1. All the calculus you've done, you know that those things are intimately related. And so the question is, are they related in a similar way for these contour integrals? And we're going to see that they are. Okay, we are going to have a fundamental theorem of, I called it in the YouTube description, complex calculus. Okay, so we're going to have a complex FTC in a sense for us. And so you're going to see that we're going to want to address that, because then it's not just whether or not the integrand itself has any issues, it's whether its antiderivative has issues at some point where you want it to be defined. Okay, so these are questions that I have to address here. So let's do an example. I think I have time for one good example at least. So let C be the semicircle. So let's C be the semicircle. So Z is 3 e to the I theta, where theta is between 0 and pi. Okay, so theta is between 0 and pi. So what does this look like in the plane real quick? Of course, in the plane, this looks like the semicircle that goes from 3 to minus 3. Okay. All right, so here's my C. Okay. So then, along the branch, let's choose a branch of the square root. All right, so if we're looking at the square root z to the 1/2, which writing this as e to the 1/2 log z, that is how we defined these fractional powers. All right, so then where's this thing defined? What branch are we talking about? So we have to pick a branch here. So if we're looking here, so of course the modulus of z is positive, and the argument of z is strictly between 0 and 2 pi. Okay. So along this branch, or I should say, yeah, this is right. So if I'm looking at this branch of this function, the square root function, this is not defined, right? F of z, right, is not defined at z is equal to minus 3. Sorry, not z is equal to minus 3. It's not defined here. Plus 3. Okay, so z is not defined at this point here. Right. Circle that in red. Okay. So there is a cut here that I'm going to redraw this picture with this missing, because the way that I have described the branch of the square root here, right, the picture is actually this thing. I'll draw it like this. So here's my negative x-axis. Here's my positive x-axis. And of course the origin's also missing. I'll put that point in red there. Okay, so I have my point C, or sorry, my point 3 here. So this is Z is equal to 3. C looks like this. And here Z is equal to minus 3. This red dotted line is the branch cut that I'm talking about. Okay, so this is my branch cut. Okay, so when we say branch cut, that is what we mean. This is my branch cut for this function. Fz is z to the 1/2, which, I've defined as e to the 1/2 log z. Okay, again, the branch in question is modulus z is greater than 0, and the argument of z is strictly between 0 and 2 pi. This is the thing that cuts out that thing. So the origin is cut out by this condition. This condition, of course, cuts out the positive x-axis. Okay, and so this is my curve C. So the thing is that what I want to stress here is the reason this is a problem, the only reason this is a problem, is because one of the endpoints here is on this branch cut. So technically, right, f of z is not defined at the endpoint of C, which is z is equal to 3. But we will see that nevertheless, the contour integral of C, over C of f of z dz is well defined. Okay. Now, without actually going through this, you wouldn't know that that's the case. And the reason you wouldn't know that's the case is exactly this issue of, look, this point that's on C, every other point on C is perfectly fine, A-OK, right? And so every other point on C is fine. And so if we chose any C to integrate along that didn't have any of its points touch this branch cut, we're good to go. We wouldn't even have to have a discussion here. Okay, but this particular C that I've chosen, one of its endpoints lies on the branch cut. So what do I do? How do I deal with this? Well, it turns out that there's going to be a way that we can handle such things. And so dealing with this is something that's going to come up in dealing with these integrals in general. So how can I do this? Okay, so how can I compute this thing? Okay. How can I compute that? All right. So first of all, let's look at z of theta. What is z of theta here? All right. So this is going to be my parametrization of C. Well, C had a very simple description. It was just 3e to the I theta. So z of theta is 3e to the I theta. All right. Theta is in the interval from 0 to pi here. Okay. What is f of z of theta here? All right. Well, this is e to the, so I'm going to write it as x so that I don't have to write everything in an exponent. So this is e to the what? 1/2 log of 3e to the I theta here. Right, but what is that? Well, using my definition of log here, this is e to the 1/2 times, this is ln of 3, right, plus I theta. Sorry. Which is moving this to, so rather distributing this and then using exponential rules, this is e to the ln of 3 to the 1/2. So this is square root of 3, right? E to the I theta over 2. Okay. Now, what do I do in order to determine that taking this contour integral is fine? What do I need? Okay. I need piecewise continuity of this thing. All right, so I need piecewise continuity of this thing along C in order to proceed. Okay. Okay. Of course, kind of combining this with the entire integrand expression, f of z of theta times z prime, I need that to be piecewise continuous. And so what I want to look at is the integrand under the definition of contour integral. So I want to look at f prime, sorry, not f prime. So I want to look at f of z of theta times z prime of theta. So what is this? Well, z prime of theta, of course, is just 3i e to the I theta. So using these things together, this is square root of 3 e to the I theta over 2 times 3i e to the I theta. That's z prime of theta. So what is this if I use Euler's formula? So using Euler's formula, this is minus 3 root 3 sine of 3 theta over 2, adding the exponents here, plus I times 3 root 3 cosine of 3 theta over 2. Okay, and theta is, if we look at this defined between 0 and pi, but not including 0, the entire thing is I want to check the continuity of this thing. So I want continuity of this thing. Although, as I said, we can actually be happier in general with less than that. Okay, but I actually only need so I need continuity of this thing. In this case, I have it. I can show first of all. So if I take limits, these are right hand limits, right? As theta approaches 0 here. Okay. These limits of real and imaginary component exist. Okay. What are they? So I'm looking at the limits as theta goes to 0 of the real and imaginary components. So as theta goes to 0, the limit of this thing is 0. Limit of this thing is I 3 root 3. So this is as theta goes to 0. So as theta goes to 0, this is 0. And as theta goes to 0 here, this is I 3 root 3. Okay. Thus, f of z of theta, z prime of theta, is continuous on the theta interval, the closed interval 0 to theta. So I can actually include 0 here. So here, I'll write this in red. Okay, so I can include that there. And this is exactly what I'm going to need in order to actually find the value of this thing, right? And so, thus, we can actually do this, right? So thus, if we define f of z of 0 and z prime of 0 to be I times 3 root 3, we can proceed. This is the kind of checking that would have to be done here to make sure that this works. Okay, so then going back to the original question, what is my integral over that c of z to the 1/2 dz? So this is then equal to, the integral from, say, 0 to theta of f prime, or not f prime, I keep writing f prime, f of z of theta times z prime of theta d theta. So what is this thing? This is 3 root 3 I times the integral from 0 to pi of e to the I 3 theta over 2 d theta. Okay. And so we can work this out on the next page where I have room. So then rewriting this, so this is the integral over c of z to the 1/2 dz. So this was found to be so 3 root 3 I times the integral from 0 to pi of e to the I 3 theta over 2 d theta. And this is equal to 3 root 3i times this integral, of course, is going to be 2 over 3i times e to the I 3 theta over 2. And this is evaluated from 0 to pi. So then evaluating from 0 to pi here, I'm going to get e to the 0, and I'm going to get e to the I pi, which is minus 1. So I'm going to get minus 2 over 3 I times, so this is going to be minus 2 over 3i times 1 plus I, if you work out the arithmetic here. Okay. Oh no, that's not. That's actually what I get from here. I didn't multiply by 3 root 3i. Sorry, that's just this evaluation here. So I still needed to multiply, and so if I do that, I get this is minus 2 root 3 times 1 plus I. There we go. Now we're done. Okay. So this is an example of kind of the sort of considerations you have to take into account when you're dealing with these integrals that might involve curves that cross over a branch cut or cross over knotty points, right, in general. So we're going to do more examples of that, and then I'm going to talk about some of these named theorems, these big facts that let us kind of sweep a lot of this under the rug in many circumstances. Okay. So anyway, that's the plan. So I will see you all tomorrow.